There is a star so large that if you placed it where our sun sits right now, its surface would extend past the orbit of Saturn. The star is called Stevenson 2-18, and according to every model we have of how stars form, grow, and die, it should not exist. Its radius is roughly 1,500 times larger than our sun's. Its volume could contain 10 billion suns. And the fact that it's out there, burning steadily in a cluster 37,000 light-years away, means something in our understanding of stellar physics is incomplete. Here's the thing that makes this worse. Stevenson 2-18 isn't alone. There are other stars nearly as large, scattered across the galaxy, all of them pushing against the same theoretical ceiling. All of them sitting in a mass range that should make them impossible. And the more we learn about them, the less sense they make. Let me walk you through why. Stars have a size limit, not a suggested maximum. A hard physical boundary imposed by the laws of radiation pressure and gravitational collapse. When a star gets too big, the outward pressure from the fusion reactions in its core becomes so intense that it starts blowing the star's outer layers into space. The star can't hold itself together. It shreds. That limit is called the Eddington limit, and it's not a theory. It's a measured threshold tied directly to a star's mass and luminosity. For the kind of red supergiant we're talking about, the math says the radius can't exceed roughly 2,000 solar radii without the star losing structural integrity. Stevenson 2-18 sits right at that line. Some estimates put it slightly below, some put it slightly above, depending on which measurement method you trust. But even at the conservative end, it's close enough to the ceiling that its existence raises a question we don't have a clean answer for. How did it get that big without tearing itself apart? Now meet the cluster that contains it. Stevenson 2 is an open cluster in the constellation Scutum, embedded in a region of space so dense with gas and dust that it wasn't fully mapped until infrared surveys could pierce through. It's young by stellar standards. Most of the stars in the cluster formed within the last 20 million years, which in cosmic terms is recent enough that some of them are still in their infancy, and inside that cluster there are at least 26 red supergiants. Several of them are comparable in size to Stevenson 2-18. One of them, depending on whose data you use, might be even larger. That concentration is unusual. Red supergiants this massive are supposed to be rare. They represent the final evolutionary stage of stars that began their lives with at least 15 to 20 solar masses. They burn through their fuel fast. Their lifetimes as red supergiants are geologically short, often less than 1 million years. Finding one is uncommon. Finding 24 in the same neighborhood suggests something about the formation conditions in Stevenson. 2 allowed stars to grow larger and live longer than the standard models predict. But the worst problem is this: we don't actually know how massive Stevenson 2-18 is. Radius we can estimate through infrared brightness and angular diameter measurements. Luminosity we can model based on temperature and surface area. But mass is harder. You need either a binary companion whose orbit you can track, or a direct measurement of the star's gravitational influence on nearby objects. Stevenson 2-18 has neither. The best we can do is infer mass from the star's position on the Hertzsprung-Russell diagram and cross-reference it with evolutionary models. Those models suggest a starting mass somewhere between 15 and 40 solar masses. But those same models also suggest the star should have lost a significant fraction of that mass over its lifetime through stellar winds. And here's where the numbers stop adding up. If the star's current mass is low, say 12 to 15 solar masses, then its luminosity is too high for its mass. It's radiating more energy than a star that size should be capable of producing. If its mass is higher, say 25 to 30 solar masses, then its radius is too large. It shouldn't be able to sustain a photosphere that extended without collapsing or ejecting material faster than it's currently losing it. Either way, something doesn't fit. First theory. The star is older than we think, and it's already deep into the asymptotic giant branch phase, where helium shell burning inflates the outer envelope to extreme sizes. That would explain the radius. It would not explain the luminosity, which remains too stable for a star in that latest stage. Stars on the asymptotic giant branch pulse. They flicker. Stevenson 2-18 doesn't. Second theory. The star formed with an unusually high initial mass, perhaps as much as 50 or 60 solar masses, and has been losing material steadily through mass ejection events that we haven't directly observed. That would explain the current radius and give it enough core mass to sustain the luminosity. It would not explain why we don't see more evidence of recent ejections. Stars that lose mass, that quickly leave behind shells, nebula, and detached layers of ionized gas. We see some circumstellar material around Stevenson 2-18, but not enough to account for the loss of 20 or 30 solar masses in the last few million years. Third theory. The star is part of a stripped binary system. It had a companion once, and during an earlier phase, the two stars exchanged mass through Roche lobe overflow. The companion pulled material away, which would lower Stevenson 2-18's mass while leaving its luminosity elevated. The companion then either merged with the primary or was ejected during a dynamical interaction with another star in the cluster. That's the most flexible explanation. It accounts for the missing mass, the high luminosity, and the lack of observable outflows. But it's also the least testable. If the companion merged, the evidence is gone. If it was ejected, it's likely too faint and too far away to detect now. The theory fits because it's designed to fit. And here is where the story widens. Stevenson 2-18 is part of a larger catalog of stars called hypergiants. These are the most luminous, most massive, and often the most unstable stars known. Many of them sit in a region of the Hertzsprung-Russell diagram that stellar evolution models label as forbidden. Not unlikely. Forbidden. The models say stars that enter that region should erupt, shed their outer layers, or collapse entirely within a few thousand years. They should not remain stable long enough for us to observe them. And yet we have examples. Eta Carinae, Rho Cassiopeiae, VY Canis Majoris, once thought to be the largest star ever measured until better distance estimates revised its size downward. All of them sit near or inside the zone where theory says they shouldn't survive. The problem is not that the stars are breaking a law of physics in the sense that gravity stops working or fusion reverses. The problem is that the models we use to predict stellar behavior are incomplete. They rely on assumptions about how quickly stars lose mass, how convection carries energy through the outer envelope, how magnetic fields interact with stellar winds. Those assumptions work well for stars like our Sun. They work reasonably well for stars up to 10 or 15 solar masses. But at the extreme end, where radiation pressure and gravitational binding energy are nearly balanced, small changes in any one of those variables can produce wildly different outcomes. And we don't have enough data to know which variables matter most. The issue is observational access. Stars like Stevenson 2-18 are rare. They're embedded in dusty regions that block visible light. They're often part of crowded clusters where it's hard to isolate individual spectra, and they evolve quickly, which means by the time we've built the instruments capable of studying them in detail, many of them have already exploded or transitioned into a different phase. The James Webb Space Telescope is starting to change that. Webb's infrared sensitivity allows it to pierce through the gas and dust that obscures these clusters. It can measure surface temperatures, detect chemical signatures in the photosphere, and track variability over time with a precision that wasn't possible a decade ago. Early observations have already forced revisions to some of the radius estimates for the largest known stars. But even Webb can't measure mass directly, and without mass, we're still guessing. Now come back to the question of how these stars formed in the first place. Standard star formation theory says that molecular clouds collapse under their own gravity, fragmenting into clumps that eventually ignite fusion. The maximum mass a star can reach through this process is limited by radiation pressure from the forming protostar. Once the protostar gets hot enough, its radiation starts pushing the surrounding gas away faster than gravity can pull it in. The accretion shuts down. That ceiling sits somewhere around 150 solar masses for a star forming in isolation. Stevenson 2-18 likely didn't start that massive, but even if it started at 40 or 50 solar masses, that's still higher than most formation models comfortably predict. One possibility is competitive accretion. In a dense cluster like Stevenson 2, protostars don't form in isolation. They're packed close together, and they're all pulling from the same reservoir of gas. The ones near the center of the cluster, where the gas density is highest, can grow faster than the ones on the outskirts. They win the competition. They hoard mass. That process can produce stars more massive than the standard ceiling would allow. It also predicts that the most massive stars should be concentrated near the cluster core, which is what we see in Stevenson 2. The largest supergiants are all near the center. The smaller ones are farther out. But competitive accretion doesn't explain why the star grew so large after it formed. Radius and mass are related, but they're not the same thing. A star's radius depends on its internal structure, its composition, and how efficiently it transports energy from the core to the surface. Red supergiants are large because their outer envelopes are cool and diffuse. The temperature gradient is shallow. Convection carries heat slowly. The photosphere balloons outward. The question is why Stevenson 2-18's envelope expanded so much more than other red supergiants of similar mass. And the answer might be metallicity. Metallicity is the abundance of elements heavier than hydrogen and helium. Stars that form in regions with higher metallicity have more heavy elements mixed into their outer layers. Those elements increase the opacity of the gas, which means photons have a harder time escaping. The star has to expand to radiate the same amount of energy. Higher metallicity equals larger radius, all else being equal. Stevenson 2 is a young cluster. It formed from gas that had already been enriched by earlier generations of stars. The metallicity in that region is higher than the galactic average. That could explain why the supergiants in the cluster are systematically larger than red supergiants elsewhere in the galaxy. But it's not a complete answer. Metallicity affects radius, but it doesn't eliminate the Eddington limit. A star can be metal-rich and still hit the ceiling, where radiation pressure overcomes gravity. Stevenson 2-18 is close enough to that ceiling that metallicity alone can't be the only factor. There's another variable we haven't fully accounted for. Rotation. Stars spin. Most of them spin faster when they're young and slower as they age because angular momentum gets transferred outward through magnetic braking or siphoned off by stellar winds. But if a star is rotating rapidly, that rotation creates an equatorial bulge. The centrifugal force works against gravity, and the star can grow larger in the equatorial plane without violating the Eddington limit in the polar regions. We don't know how fast Stevenson 2-18 is rotating. The star is too distant and too obscured for us to measure rotational broadening in its spectral lines with current instruments. But if it's rotating even moderately fast, that could buy it a few hundred extra solar radii before instability sets in. The catch is that rapid rotation also makes the star more likely to shed material through equatorial outflows. And again, we don't see strong evidence of that. The star is losing mass, but not at the catastrophic rate you'd expect from a rapidly rotating hypergiant on the edge of the Eddington limit. So we're left with a star that's too large, too luminous, or too stable, depending on which measurement you trust and which model you apply. And the universe has made at least 24 more just like it in the same cluster. Here's the piece that should haunt you. Stevenson 2-18 will not stay this size for long. Red supergiants in this mass range have lifetimes measured in hundreds of thousands of years, not millions. The star is already near the end. It will either explode as a supernova or collapse directly into a black hole, and when it does, the explosion will be visible across a significant fraction of the galaxy. But before that happens, we have a narrow window to study it, to measure its spectrum, to track its variability, to model its wind, to figure out what allowed it to grow this large in the first place. Because the answer to that question isn't just about one star. It's about the upper boundary of stellar mass, the conditions that allow the largest stars to form, and whether the models we've built to describe stellar evolution can account for objects this extreme. Right now, the models can't. They accommodate Stevenson 2-18 by stretching their assumptions, by invoking rare formation scenarios and fine-tuned conditions. But they don't predict it, and a model that doesn't predict the existence of something we can see and measure isn't complete. This star is a boundary case. It's an outlier that's testing the edges of what we think we know. And every time we point a more sensitive instrument at it, the data we get back makes the picture more complicated, not less. Thanks for watching, and I'll see you in the next one.